Hello everyone, this is Dilip. In last video, we have seen how to write code to implement neural networks. And in today's video, let's look at the diagnostics part. These diagnostics are required because the goal of either linear regression or logistic regression or neural networks or any other machine learning problem is to calculate the weights or parameters which are part of hypothesis. And it's our goal to get a better hypothesis. So we look at diagnostics, which will help us get a better hypothesis. Let's go back to our earlier simplistic linear regression problem, where size of the house determines the price of the house. And if we derive the hypothesis based on our training data, we might get a hypothesis like this. This is ignoring regression for now. And even if we have regression, there is no guarantee that our whatever the hypothesis we derive, it will generalize for the given training data. And if we give new set of data, which our code hasn't seen before, and if we use our hypothesis, the hypothesis will fail to work on the newer data, which it has not seen, because it has high variance problems here. So we could think of what could have gone wrong in deriving our hypothesis. One immediate thought which can come to our mind is there is less training data. That's why our hypothesis failed to generalize for newer problems. And what more could be the reasons? We can start using the more features. So if we have lesser number of features, we can start adding more features. Like for our previous slide, we can start adding the data like location of the house, like how much distance it is from the road, the number of floors in the house, etc. Or we can start using lesser number of features. Say if we have 1,000 features and not all of them are useful, so we can remove the useless features. And we can use a higher order polynomial. We can think of, say, a single degree polynomial is not sufficient. We can go for quadratic or cubic, or we can go for lower order polynomial. Say we are already using a cubic equation, and we can think like having a lesser order is better, or using a bigger regularization parameter lambda or a smaller regularization parameter. So all of these can help us in modifying our hypothesis. But whether the hypothesis works better or not, we don't know. So we can just keep doing trial and error. Like we can keep training more data, and we can start experimenting with more features, less features. So this is all a trial and error method. Instead of doing this trial and error method, if we have diagnostics, which can take some time to implement, but it will help us derive a better hypothesis, this will obviously save time instead of going for trial and error, trying all these methods on our hypothesis. So how do we do that? Say we have a training data given here, where we have 8 number of data, size of the house and price of the house is given. What we can do is we can split this training data into 2 parts. One is training data, other one is test data. So we will derive our hypothesis based on the training data. And that hypothesis, whatever we derive based on the training data, so this is h of x. Yeah, it's not coming because I'm using the mouse, but think of this as h of x. So what are the hypotheses we derive? Then we can use it to calculate the cost function. On the test data. So in the test data, we can use the same cost function and iterate over all the test samples and see how much is the cost function will result in. And we can take one more hypothesis, say modify the hypothesis a little bit, and again train it. And then we can input the same newer hypothesis and again take the cost function. And whichever gives us the lesser cost, that will be the better solution. Like that will lead us to better hypothesis. So this is for linear regression. So in linear regression, we can use the same cost function which we use for training the data, but we use the cost function to iterate over test data only. And the usual split we do is 70% of the data will be training data, whatever the data we are given, and 30% of it we put as test data. And it's always better to have more percentage in training data. The reason being, our hypothesis derivation will be better. Now we have seen linear regression problem, how to have the diagnostics there. Let's move on to logistic regression. In logistic regression, we know our hypothesis will result in a value between 0 and 1. And if it is less than 0.5, 0 is the result. Let's imagine like we are just working on the binary classification problem now. And if our hypothesis is greater than or equal to 0.5, it is 1 is the result. Now, what will be the error here? Now, if we again split the data into training data and test data, and in test data, we start looking at the error part. So in test data, it will be an error. Say error will indicate by 1, or error will, let's say error will have the value of 1 for a given test data, like for a given record in the test data. If h of x is less than 0.5 and y equal to 1. So this is a case of misclassification, because h of x is less than 0.5 means it is identifying it as 0, but it is of class 1. If h of x is greater than or equal to 0.5, it is identifying it as class 1, but it is of class 0. So this is the error. So whenever we see the error, what we do is we put for that particular record in test data, like for that particular one test data, we'll put the value as 1. Otherwise, there is no error, 0. And once we have these error values for all the test data, what we do is we do a summation of all the errors for all the test data, and we divide it with total number of test samples. This will give us the average error that our hypothesis resulted in. And whichever hypothesis gives us the less error, that is a good hypothesis. Since this is binary classification problem, so I'm having the error like this. And if you go for multi-class classification problem as well, there also you can put the error value as 1 if it misclassifies the given test data, and we can put as error as 0 if it doesn't misclassify. That way we can calculate the error in multi-class classification problem as well. As you can see, this we can extend to neural networks as well, because there also in the end, it is a hypothesis, whatever the output we get, and then we can calculate the error value, and then we can average out the error value there as well. So once we derive the hypothesis, depending on the test data, there is a chance that our hypothesis is biased towards the test data. And the way to overcome that is to use the cross-validation data. What we can do is, instead of splitting our training data into training data and test data, we can split it one more time to have the cross-validation data as well. So this whole data we can split into three parts. One is for training data for getting the hypothesis, one is for cross-validation, and one is for testing. So once we get the cross-validation error, and based on that we derive the hypothesis, then again we can use the test data to derive a better hypothesis. This way we can be sure that our hypothesis is not biased more towards a particular test data. And this is the usual split we do. Given a set of training data, we split it into 60% we put as training data, 20% as cross-validation data, and 20% as final testing data. So this is how we derive the better hypothesis in the end. And in the industry, most of the times people don't follow this, and they will stick to 70-30, where 70% they put as training data and 30% as testing data and just be done with it. But if you can implement this way, this will result in a much better hypothesis than compared to using 70% training data and 30% test data. Thanks everyone for watching the video. Bye.